Networks are not collections of homogeneous links and nodes that can accept any path for any service. The real world imposes risk and cost constraints that need to be part of our model. In this video, we'll look at two new ways to constrain service paths. The scenario we're going to use imagines the infrastructure between two sites or buildings. The buildings are linked by two parallel bidirectional links to provide adequate bandwidth. However, the links are carried in the same trunk between the two sites. This means that any external cause of failure of one link would very likely impact the parallel link. There is also a very expensive satellite link available with standby capacity for critical services. In this situation, we can model shared risk groups for the infrastructure that's linked by some external threat. The SRG can be used to influence routing of the protection paths and disjoint services. The scenario file provided for this exercise is called srg protection disjoint scenario.spb. Remember, to import a .spb file, you need to choose the iVNT GPB collection plugin and use the .spb scenario import adapter. The model shows that the links between building A and building B have a maximum bandwidth of 100 available and a cost of 3. The satellite links each have a bandwidth of 100 available and a cost of 10, making the total cost of a satellite service path 20. I've used dashed lines to show the satellite links. The other links all have lower capacity and lower cost. There are two services configured. P2P1 and P2P2 each link building A with building B. They both require minimum hops and minimum cost. P2P1 requires protection for nodes and links and for SRG, shared risk groups, and must be disjoint from P2P2. P2P2 has no requirement for protection. In this topology, the source node for P2P1 and P2P2 at the top of building A is marked as a source node, and the destination at the top of building B is marked as a sink. To begin this exercise, I'll pin the P2P2 service. When you pin a service, it's frozen out of the path computation. You can pin a service that's not been computed so that it has no influence on routing other services and consumes no bandwidth. Alternatively, a service can be pinned after it's had a path computed. In this case, the path and bandwidth consumption are fixed and cannot be changed when the model is reset and recomputed. By pinning P2P2 now, I'm preventing it from consuming bandwidth and from influencing P2P1's need to be disjoint from it. Now we can compute a route for just P2P1. The working path and protection path use the cheapest route. So let's model a shared risk group. In the modeling window, we go to the Groups tab to create the new group. We add the links to the group using the right-click context menu. It's also possible to add nodes or links to a group by right-clicking on the group name in the modeling window. Now if we reset and recompute the path, the protection path is forced to use the satellite link to avoid both the working and protection paths using links that both belong to the same shared risk group. Now I'll unpin P2P2 and recompute. The working path for P2P1, protection path for P2P1, and the path for P2P2 all take separate routes. Now I'll require protection for P2P2. This time, when we compute, only one service can route successfully, as there are not sufficient paths available to provide working and protection paths that are disjoint. In my result, P2P1 fails because it can't compute a protection path. But your computation may provide a different but equally valid result. Unless we change the topology, we can only solve this by relaxing a constraint. For example, we can make the satellite nodes and satellite links disjoint exempt. This means the working paths can remain disjoint, but the protection paths will be able to route successfully via the satellite. So with the satellite and its links disjoint exempt, both services, with 3 paths including the protection path, can route between the buildings. Now we'll reuse this topology and look at subnetworks. I've removed the shared risk group, the disjoint exemption, and the 2 P2P services from the scenario, leaving just the topology. We'll look at subnetworks as a different way to influence routing. I'll create a subnetwork containing building A's nodes and links. They're all added now. Clicking on the group name highlights them to check. Now I'll add a service that starts and ends in the subnetwork. It requires minimum hops and minimum cost, and I'll also tick Route within resource group. This tells the routing algorithm not to route outside the subnetwork. Now let's route the service. Not surprisingly, the computed route is the most direct path. To show the effect of subnetworks on routing, I'll take some links out of service and reset, then recompute. Although a path is available via building B, the routing fails. If we look at the path properties for the service, the failed constraint is route within resource group. To prove this, I'll remove the constraint and reroute. We can see that the path now goes via building B, and it's now a valid path. This method of constraining routes has some limitations. If you construct multiple overlapping subnetworks, the routing algorithm can't be told which subnetwork to use if a service starts and ends in both subnets. An iCustomize script is required in this case, or the constraint can be enforced using affinities instead of or as well as subnetworks. Shared risk groups and subnetworks can be used to make networks more efficient and resilient. You should construct some new scenarios to experiment with these two iVNT features and examine their effect on optimizing service paths. If you have any questions about iVNT or the iVNT training, please contact ARIA Networks during UK office hours.